Well, good morning, everyone, and welcome to today's JKMRC seminar for Friday, the 1st of October. My name is Nathan Fox from WH Biomining and Geology Research Centre here at the University of Queensland. Welcome, everyone, and thanks for joining us online today. Before we begin, on behalf of the University of Queensland, based here in Brisbane, we would like to acknowledge the traditional owners of the lands on which we meet today. We pay our respects to their ancestors and to their descendants who continue cultural and spiritual connections to country. We recognise their valuable contributions to Australian and global society. So today it's a pleasure to introduce today's speaker, Dr. Tobias Schlegel from CSIRO in Perth. Tobias has worked extensively in iron oxide copper-gold systems in both the Gawler Craton of South Australia and the Cloncurry region of Queensland. His research integrates field studies and laboratory work to investigate the formation of ore deposits. His focus is on geochemistry, applied mineralogy, and the interaction between hydrothermal fluids and rocks during mineralisation. Tobias obtained BSc, MSc, and PhD degrees from ETH Zurich, and he has held research positions with ETH Aachen University and now as a research scientist with CSIRO Mineral Resources based in Perth. Today's talk is really relevant to Queensland. He's going to be discussing his recent work at the Ernest Henry iron oxide copper-gold deposit, showing some results from SEMT analysis and portable XRF measurements to unravel this complex but really significant deposit to Queensland. Tobias's talk is called Mineral Zonation at the Ernest Henry iron oxide copper-gold deposit, Implications for Deposit Formation and Exploration. So, Tobias, over to you. Thank you.
Well, thank you very much for this introduction and welcome everyone to this talk. I would also like to acknowledge traditional landowners from the Whadjuk people of the Noongar Nation, and I pay my respect to the elders present, past and present and emerging. As Nathan introduced, so we talk about the mineral zonation at the Ernest Henry IOCG deposit. And what you see on the right side is basically a block model of the Ernest Henry area, of the Ernest Henry deposit. And this illustration on the right is based on published papers from March 2006. So everything I did is basically took his publication and sort of redrawn a block model. What I'm going to present today is a lot of data and not that much interpretation. The data was sort of acquired during a large project, the Cloncurry Metals project, which was financed by the Geological Survey of Queensland and as part of the Queensland government and co-funded by CSIRO. After a really short synopsis of iron oxide copper-gold deposit features, I will have a closer look at the geology of the Ernest Henry deposit. I'm sure many of you are much more familiar about the deposit, so I will keep relatively brief. I will touch on how we determined the modal mineralogy in samples upon which the mineral zonation is based on. The instrument we used is a so-called scanning electron microscopy test scan integrated mineral analyzer. Complex word, but it's actually not that complex. I will present the mineral zonation, a number of mineral maps, okay, and characteristic mineral replacements we observed in samples from the Ernest Henry deposit, and finish up with the comparison among mineralogical and traditional geochemical data obtained from whole rock assay data and portable XRF. So all IOCG deposits show abundant magnetite and/or hematite. They show a zoned alkali-calcic iron alteration. And importantly, this sort of alteration is part of the definition of IOCG deposits. And it is at least partly based on the published alteration zonation that has been put out from Ernest Henry, featuring the importance of albite and K-feldspar-rich alteration, or let's say K-feldspar iron oxide-rich alteration. We will see that this interpretation is not really complete because an important alteration component is actually missing. And we're going to look into that in detail. The deposits, or in general, they show a scarcity of sulfides, in particularly iron sulfides like pyrite or pyrrhotite. The ores are usually hosted in discordant, structurally controlled breccias, veins, and are often essentially replacement bodies. And there is typically no clear genetic relation to an underlying intrusion. And if or if there is, like Olympic Dam, if there is an intrusive body, there is no clear, let's say, spatial connection to it. So they form typically in sort of a distal environment to an intrusion. IOCG also form in a range of tectonic settings, ranging from a subduction arc to back arc, for example, in the Andes, to continental rifting and transpressional to transtensional settings or crustal settings like we have in the Ernest Henry area. This sort of illustration we published last year, and you see already from the color scheme showing the distribution of alteration patterns that Ernest Henry appears to be a bit different compared to the rest, just because there is more blue and purple than red and orange. We will see that this has to change. So part of this figure, although it's only 1 year old, is actually already wrong. The Ernest Henry deposit is located at the boundary of the eastern fault belt as part of the Mount Isa inlay. The deposit is concealed by approximately 50 meters of Phanerozoic cover and does not outcrop. Okay, the ore body is basically made out of magnetite, or let's say iron oxides and chalcopyrite, and is sort of a pipe, elongated pipe shape. And this ore pipe is essentially hosted in a much larger breccia body. The deposit is hosted within magnetite K-feldspar alteration, or altered rocks. And the host rocks are typically intermediate metavolcanic to mafic metavolcanic rocks of the Mount Fort Constantine volcanics. To the south, we have the Ernest Henry metadiorite, which is partly altered or albite altered, and then to the south, and then in the north, we have metasedimentary rocks of the Corella Formation. As I said, many of you are probably more familiar with the geology of the area. So we really looked at the deposit and not at the regional scale. This illustration here on the right shows representative images of typical rocks and ores from Ernest Henry. And to be clear, I copied this image straight out of a thesis authored by Sean O'Brien at the University of Adelaide. And Sean, if you're out there, please forgive me. So I used your image, your slide or your image, but I couldn't find anything better. We see variable albite and K-feldspar altered metavolcanic rocks and essentially breccias. Seagull tension waned breccias and more or less reddish, greenish, orange colored rocks, which are typically what is typically called as red rock alteration, and it's very hard to determine whether it's the red rock. The red color is actually albite or K-feldspar. We see that the chalcopyrite is typically hosted in the breccia matrix and to a subordinate degree in the clasts as well. The high-grade ore is sort of a matrix-supported breccia, whereas the low-grade ore has has a higher clast component. In the center here, we have a sort of a typical cross-section of the Ernest Henry deposit, with the ore body here in the center bound by 2 or 3 shear zones. Okay, and what is relatively new is sort of this interlens, which is part of Sean O'Brien's thesis. He described that in detail, and who has not read this thesis, I strongly suggest that you give it a go. I think it's very good. So the early mineral paragenesis work was done by Jody Mark et al. At JCU back in the mid-2000s, and you might have seen other versions of this mineral paragenesis. However, this one shows that we have an early sodic calcic alteration event, and it's overprinted by sort of a K-feldspar magnetite or iron oxide rich alteration event. The question here really is, what is missing? Okay, and well, usually in all these paragenesis diagrams, the effects of iron oxide alkali calcic alteration on minerals is missing. So we don't really know what is replacing what, but for the development of an alteration zonation, or to explain the alteration zonation, this is really crucial. So because the mineral replacements define the sequence of hydrothermal alteration, which might lead to higher grades of copper ore. An important alteration mineral which is missing in this sort of in this paragenesis diagram is chlorite. And I can only speculate why chlorite is missing in the original work, okay? And you have to think of how this paragenesis work is typically done, okay? Considering the classical petrography is typically done on transmitted and reflected light microscopy. So, and if you have never looked at iron oxide copper gold ores, okay, then I'm going to show you this. I'm going to show this image. Petrography is typically very hard, okay? So what we see here is a hematite breccia, not from Ernest Henry, from another place. Also an IOCG deposit, and it's a photomicrograph in transmitted light. And what you see is awful a lot of black, okay? And on the right, you see the same image in the reflected light. And I would argue that it's pretty bloody difficult to determine what are the minerals. Obviously, we see that there is some hematite here, there is some chalcopyrite, then a large gray zone, which might be quartz. There is some greenish stuff, which might be sericite. But everything sort of in between in the matrix interstices is very hard because you just don't see it. And that's why you can easily miss minerals in your paragenesis. The way forward is we determined the modal mineralogy of about 270 samples from 8 drill cores. And we determined this mineralogy by the SCM TEMA, the scanning electron microscopy test scan. That's the company, integrated mineral analyzer. And we see here sort of an illustration of the Ernest Henry mine area with the mine pit, okay? And then the orientation of the 8 drill holes, cross-cutting to the mine sequence, and the sort of pipe-shaped ore body. And what we see here in orange is sort of the 1% copper ore shell. So we see that some rocks, some drill cores, they cut the host rocks, others cut the deposit. On the right, so let's go into some results. On the right, you see the typical samples. There are 2.5 centimeters diameter plugs of drill core. And on the right, you see the typical mineral abundance with very abundant minerals like feldspars, micas, chlorites, sort of abundant minerals, with, for example, siderite or muscovite, as a white mica, and minerals which just are present in some samples like fluorite or allanite. So mineral identification is typically based on an SCM EDS X-ray spectra matching with the mineral reference spectra using the TEMA software. And what we see here is basically a signal, okay? And when the in green, when the SCM signal or the EDS signal matches the reference spectra, the software sort of assigns a mineral and assigns a color. And this is how these maps are made. This diagram here basically shows the results of the SCM TEMA data. And let's have a look at it for a while. So on the right, we see a downhole plot of samples from one drill core, drill hole EH691. That crosscuts the Ernest Henry ore body. And what we see, we illustrate the mineral abundance in volume %. So column 1 shows the sample location with respect to known shear zones and the breccia body. Column 2 shows a simplified lithology logging based on company data. So with red is the metavolcanic, metasedimentary rocks, and albitite. The third column shows the alteration footprint. And this is sort of an interpretation of the mineralogy data. With distal alteration footprint in green is the medial, then the proximal, then sort of the marginal ore zone, and the central ore zone in purple. And these columns here show the actual mineral abundance, okay? In a column is all the time the same mineral. In a row is sort of the modal mineralogy of one sample. And it's all for mineral abundance greater 0.02 volume %. Okay, a separate color code is used for each column, and warm colors indicate high values. Okay, the bars here, of course, indicate higher pyrite and chalcopyrite degrees contents. So what you should see, first of all, you should sort of see the ore body here. And the ore body obviously has a lot of chalcopyrite. And what else you should see is a broad zonation between albite, scapolite dominated rocks at the top and at the bottom, okay, turning into more biotite as part of the potassic alteration, then into more K-feldspar, okay, and then eventually the marginal ore zone contains more muscovite, and then into the central ore zone. So basically the mineral zonation is a funnel-shaped distribution of alteration minerals, and this funnel-shaped distribution is indicated by this gray hedged area. So the illustration indicates that actually the accurate detection of mineral gradients may be important in localizing copper grades during IOCG target evaluation. Another important feature is that we see that the ore zone, on both sides of the ore zone, you basically have alteration halos of apatite and pyrite, which extend hundreds of meters into the host rocks. Let's see how we go with time here. All right. And now I would like to show you a few mineral maps, okay, that are characteristic for the different alteration footprints. And this one is here, is a characteristic of the distal alteration footprint. We see lots of albite in sort of blue-gray on my screen here, that is intergrown with magnetite, a bit of titanite, and is cross-cut by a vein of calcite and pyrite forms at the alteration at the vein selvage story. And the beauty of these mineral maps is that you actually can do petrography on it. You can establish timing relationship, you can establish replacement, mineral replacements. Let's look at the medial alteration footprint. We see again albite intergrown with magnetite, and then sort of decay feldspar alteration comes in with the formation, so the potassic alteration comes in with the formation of biotite intergrown with lots of magnetite in that case. So all of this is actually straightforward and nothing new about it. It's all published, but maybe not as well illustrated. Here we go to the proximal alteration footprint, and that's a characteristic image of that. And we see again also early albite-rich rocks that sort of, well, the evidence of albite-rich alteration with superimposed by this K-feldspar rich alteration here in sort of orange-red. And finally, infill of calcite into open voids. Again, this is nothing new. Sodic alteration overprinted by potassic alteration, in that case, K-feldspar. If we go to the marginal ore zone, the picture looks a bit different. And this picture shows evidence of hydrolytic alteration. So what is hydrolytic alteration? It's typically when minerals react with acidity, H+, to form, in that case, white mica and quartz. Okay, chalcopyrite is intergrown with K-feldspar, albite, quartz, chlorite, muscovite, and essentially calcite. What is important here as well, also note the abundance of anhedral quartz, okay, in gray, which results when K-feldspar reacts with an acidic fluid to form muscovite. So it's basically a redistribution of silica from the K-feldspar into quartz. Looking at the downhole, yeah, we saw that. Anyway, let's go to the next one. The central ore zone is another image of that, with lots of K-feldspar, a bit of anhedral pyrite, and then the breccia matrix made of hematite, magnetite, and in that case, chalcopyrite and late infill of carbonate. And we see again that this K-feldspar is actually really intergrown with chlorite and chalcopyrite. If we zoom into the center here, we see another feature which is characteristic for IOCG deposits, and that's the replacement of pyrite or early sulfide, iron sulfides by chalcopyrite. So we see here the anhedral shape of pyrite and then replaced by this reddish mineral, the chalcopyrite. The last image from the central ore zone is basically is basically an intimate intergrowth of residual K-feldspar, clinochloride, chlorite, magnetite, hematite, quartz, anhydral quartz. You see that beautiful, nice crystal shapes projecting into the open voids. And that also indicates that some of the calcite is sort of thin ore, but also outlasts the chalcopyrite precipitation. This image here is a visualization of the plain modal mineralogy. And what we see here is 100% stacked bar plots of feldspars, okay, with respect to the alteration footprint. So when we see that the top of the drill hole is essentially albite altered when we speak about feldspars, and then the relative abundance of feldspar changes towards K-feldspar rich rocks, okay, towards the ore zone. And important, the bottom is actually not albite altered at all. So the albite alteration is actually not surrounding the ore body, but it's more concentrated at the top of the ore body. At the same time, we see a combination or a stacked bar plot of the relative abundance of chlorite, of biotite chlorite and white mica. And this is probably the most beautiful image or illustration. You see very abundant biotite, and then the biotite sort of, the biotite amount decreases towards the ore body. Okay, it's where chloride picks up, okay, and then the marginal ore zone is sort of bound by this white mica envelope. We also see that the composition of the chloride change, and from clinochlore dominated to chamosite dominated chloride, and then back to clinochlore dominated towards the ore zone. In the back here, okay, we have basically measurements from portable XRF and a gamma ray spectrometer. And what we see is that just by simple maximization of phosphorus, manganese, arsenic, and uranium from the portable XRF, but also from the gamma ray spectrometer, and we sort of find the copper-gold ore body here at the center. I touched on this before, that the amount of quartz increases towards the ore body. When we see here, when we see here, the amount of quartz increases towards the ore body significantly, okay? But actually, the silica SiO2 content remains stable, plus or minus stable. And this actually shows that silica is actually just reshuffled from feldspars and biotite into quartz. So the albite alteration is seen in the sodium over aluminium ratio, and this, of course, you can only see in assay data. And yeah, and the K-feldspar alteration is seen in assay data, but also in portable XRF data, which is sort of important to see. So what I present you two slides showing characteristic mineral replacements, and what we see here is one mineral replacement that I just introduced. It's basically the replacement of biotite here in brown by chloride. And we saw the effects in the downhole plot. Sorry here, and this one here, and this sort of photograph shows you what's actually happening on the minimal map scale. The other one is the alteration of magnetite to hematite. And we see a reflected light image from the ore zone at Ernest Henry. We see lots of magnetite here in sort of brownish gray, replaced by hematite, and an awful lot of holes, okay? And these holes are subsequently infilled by chalcopyrite. We skip the lower part, it essentially shows the same. So, and if we put this, or if we try to put this in some reactions, then when one can tentatively say, well, this sort of replacements are the results of hydrolytic H+ alteration reactions. So when magnetite reacts with an acidic fluid, you can create hematite and a bit of iron 2+, which goes into the fluid. The same thing works for biotite to chloride replacement. So biotite reacts with an acidic fluid to form chloride and quartz. Okay, so you take the silica and you form quartz. The same thing is when you turn K-feldspar into muscovite and quartz, you release basically quartz. And this is why the quartz amount increases towards the ore body, but the silica actually remains stable. No talk without a cross section, okay? And so this is a cross section through the Ernest Henry deposit. And it basically goes to the center of it. And then we're looking west. What we see is so the outline of the breccia body here in the dashed lines here. Okay, with some simplified geological logging. So all the metavolcanic rocks are essentially in white because I want to plot some data over it. Then we have the copper grades with blue low grade, red high grade, and here we have 3 drill holes and basically the sample location of these three drill holes. And then here the cross section, another cross section. So basically which cuts the breccia pipe perpendicular. And this is what we see here. So it's one that goes like this and one that goes like this. And we see basically that the breccia zonation is larger than the actual mineralization. That's an important thing to note. Here I plotted the distribution of the feldspar into the section. And we see beautifully that the central ore zone at the top here is essentially K-feldspar altered. This one we looked at, so there's an albite alteration at the top, but basically no alteration at the bottom. And if we go to the second section, cross-cutting this, we see the same drill hole, the same data, and parts of another drill hole, which sort of is more towards me. What is an important feature here as well, that we sort of track the interlens, okay, the unbrecciated and unmineralized interlens, and this interlens is essentially not altered when it comes to feldspar. This is sort of straight. This is consistent with what Sean O'Brien has written in his thesis. Here is the distribution of the phyllosilicates. We see characteristic variations in the relative abundance of biotite and chloride. And this is really, this is the important thing, you see it way beyond the limits of the ore body. So if you can track this, you potentially can navigate towards the ore body or towards the Ernest Henry ore body. Here we have a sort of a new slide. That's the distribution of the iron content, okay? White is low iron, black is high iron, and this sort of colored thing sort of track the amount of the hematite overprint. We couldn't measure this, but this was just examining or looking at all the samples and examine, is it a weak hematite overprint or is it a strong hematite overprint? This line here, the black line sort of shows the magnetic susceptibility, and we see that where the hematite overprint is, there is actually a lower magnetic susceptibility, which is consistent with the logging or with the replacement of hematite, but it's seen in data. And this is the ore zone here, based on assay data from the company. You can also track it with just simple portable XRF measurements of copper. Here again, in the perpendicular cross section, sort of the same features. Areas with high hematite overprint, you have a lower abundance or a lower magnetic susceptibility. So this is sort of the last slide. That's how we see we go with time. I give you, yes, that's good. The mineral data on the left here shows that sheet silicates are dominated by chloride and minor phengite. What I made sure to say here is that this data is colored according to the alteration footprint, with purple central ore zone and blue the distal ore zone. So we see that the samples from the ore zone actually show chloride. Okay, and if you go to the medial alteration footprint, consistent with what I presented before, sort of you have biotite dominated mineral samples. Sorry. In the middle diagram shows the results of the portable XRF And they're largely consistent with the mineralogical findings from the SCM team. However, the important difference here is the chloride is sort of underestimated. Okay, that's because we're looking at sort of whole rock as data from the surface. It's important that the portable XRF data was measured on the same surface than the SCM TEMA mineral maps. But the portable XRF sort of tracks or sort of gets the alteration right, because it is you can determine the white mica out of these measurements. This is a very different in the whole rock assay data. Okay, and the difference between the three is that this is a data point from a volume of rock. Okay, and if we look at the volume of rock, then you get an impression that the rocks are actually dominantly K-feldspar altered, especially in the breccia, in the sort of central ozone. And this is only part of the story. Okay, yes, the clasts are K-feldspar altered, but not the matrix. Remember, the matrix is dominated by chloride and hematite and partial hematite alteration of magnetite, sort of this hydrolytic alteration. So why is this so different? Okay, the difference is as I said, in this volume approach. So when you analyze a 1 meter assay, a whole rock assay data, then the clasts, K-feldspar altered clasts, impose their chemistry onto the data point, or onto the chemistry. And this is why, if you just look at petrography, where you cannot really determine the minerals, and then combine it with interpretation of whole rock assay data, you are going to miss, or potentially miss, the really important alteration, which is the hydrolytic alteration. So the difference is that you would look for K-feldspar altered rocks, okay, but the breccia matrix actually shows that the mineralization is at least partly associated with feldspar, K-feldspar, and biotite and albite destructive alteration, which is quite of a difference. This brings me to the summary. So the Ernest Henry deposit shows a distinct alteration mineral zonation, which can be explained by a sequence of iron oxide alkali-calcic alteration. And then the important bit, this alteration, or the sequence of alteration, is superimposed by hydrolytic alteration. And I showed that the hydrolytic alteration is likely involved in chalcopyrite mineralization. And from an exploration point of view, the SCM TEMA technique accurately maps the zoned hydrothermal alteration and allows vectoring towards mineralization from drill core data. This can be combined with handheld tools, for example, a portable XRF and the gamma ray spectrometer. And you want to maximize uranium, manganese, phosphorus, and arsenic to actually sort of direct you towards higher copper grades if you explore in IOCG breccias or if you do early drill target evaluation. And I close with that. Thank you very much. And I'm happy to take your questions.
Thanks very much, Tobias. That was a really great talk. Thank you for providing an update on your work, and it's built into a really great compendium of knowledge on that really important deposit here in Queensland. So I'm just struggling to get my mouse to switch on the video. Thanks again. So if there are questions from anybody online, please use the question and answer box and we can pose those to Tobias. We already have one that's come in from, excuse me, Mark Annenberg. And his question is, how does calcite relate to the hypothesized influx of acidic fluids? Is it the unreacted residue or maybe something else? I don't know if you can comment on.
Pardon, is it the
top question there? You might be able to see the question and answer book. So just really just relating to the potential origin of the calcite at Ernest Henry.
Yeah, I mean, early fluid inclusion work from Ernest Henry showed that apparently the mineralizing fluid are CO2 rich, and sort of our petrography maps indicate that at least part of the CO2 is related to chalcopyrite mineralization. Okay, but calcite is also in most sort of petrographic settings is post-dating mineralization, or at least outlasting mineralization. So this is a bit tricky question where petrography tells you some things but not everything. But definitely a significant part of the calcite is actually laid.
Okay, excellent, thank you. We have another question here. I guess this is something that was planned on my mind. Evelyn Mervyn from Anglo just has the question of whether you've considered core scanning data to identify some of the minerals. I suppose given that a lot of the minerals that you're tracking are active in the or hyperspectral data sets, what would you miss with 1 millimeter mineral mapping versus the SEM-TEMA approach? So a slightly coarser resolution.
Yeah. I would say it depends on what technique you use, okay? So with the SEM-TEMA, we scan at the 10 micron resolution, okay? And so that's why we get also the very fine grain minerals. But if you measure, for example, with the high logger or with the core scan in sort of the hyperspectral space, then first of all, you don't get modal mineralogy, you get only relative abundance of minerals, and the different wavelengths, it's really hard to combine them, at least to my knowledge. So yes, you get minerals, but not a complete minerals, and you cannot really track the mineral abundance the way that the SEM-TEMA can. In terms of resolution, well, if your rocks, and we work with breccias, sort of tell you that you should work in the sub-millimeter resolution, then I think the rocks should determine the analytical technique. But I mean, there is people out there who will say, well, this takes too much time, okay? Because a downside of the SEM-TEMA analytics is basically the sample prep, okay? So you need to have a polished section or polished plug, and then so the runtime for one analysis is about 2 to 2.5 hours, depending on the scanning resolution. If you scan with 20 micron resolution or 30 micron resolution, if you think that's enough for your rocks, then you're done in 20 minutes, half an hour.
There's a huge amount of value add that you can get from the SEM-TEMA data, though, if you share amongst other groups that don't keep the data to yourself and make it more available.
The beauty of this approach here is actually, so we analyzed, that was a 600-meter drill hole, so it's a longer drill hole, but we analyzed the 600-meter interval with 47 samples, and in this sort of setting, we tracked the alteration. So this actually shows that you not necessarily need, especially when you explore in IOCG breccias, that you not necessarily need every meter a data point or every centimeter a data point. What's it going to tell you? Well, it tells you very detailed, but you might be actually overwhelmed by the amount of data.
That data mining approach, have you considered doing any textual analysis of the mineral phases or of the actual kind of entire pucks that you've analysed, just to understand whether or not you're looking at assemblages that are related to breccias or to veins and how that fits in the overall paragenesis?
Yes, we have done this. I mean, I've done it basically on all the 270 samples. I tracked I logged the mineral replacements. Okay, I sort of have a feeling what's coming earlier, what's coming later, and I was only able to show a few examples. Otherwise, I can show you 200 mineral maps, which is a bit boring. But for example, and this is where maybe future goes to, I don't think there is an automated way yet.
Okay, so I think that is a good kind of avenue to go to.
So automated petrography, yeah, something.
Talking of petrography, we've got a question here from Rowena Dugworth. I might just go back to Paul's question first, because he got in there first, then I'll read Rowena's and we'll pose that. So Tobias, Paul's just asking if you could discuss the origin of hematite-dusted feldspar that's quite common in the Cloncurry district. Does it relate in any way to the replacement of magnetite by hematite?
Difficult question. I think part of the hematite dusting is just when you sort of, in the earlier replacements of, for example, hematite dusted albite, when you replace the rock for plagioclase, for example, the tiny bit of iron, which is sort of everywhere in a way, just gets liberated and dusts your rock red. But if you look at these rocks and if you actually assay them, usually the hematite dusting, let's say if you compare non-hematite dusted with hematite dusted one, certainly depends on the degree, but there's usually not a big change in iron content, at least to what I have seen. But yeah, the hematite dusting makes the recognition of albite and K feldspar quite difficult.
Absolutely, it's always going to be a problem. So just going back to Rowena's question, it's kind of also a comment. So Rowena states that she's just been finishing up a petrographic study at Ernest Henry as well, and she agrees with your observation that the chlorite is coming after the biotite, and that it's obviously easy to see petrographically. Now, it appears to be paragenetic related to the later calcite and apatite, and Rowena is just wondering whether that fits with the data that you've seen from the SEM team as well, or your overall model for the formation of the deposit. So
I mean, so what was the question?
It's more whether or not the chlorite after the biotite being forming an assemblage with calcite and apatite, does that fit with your model?
Yeah. I mean, yes, it does. Yeah. I mean, the important bit here is that you, especially relating apatite to the alteration, is what one has to determine why there is so much apatite. What is actually why do you have an alteration halo of apatite intergrown or sort of coexisting with the replacement of biotite and feldspar to chloride? Because the apatite simply tracks the alteration of feldspars and biotite. If you look at the petrographic images, not only at Ernest Henry, you can also look at this at other prospects, for example, like Triton in the Gawler Craton, when we published even an image for that. If you replace feldspars, okay, then the apatite forms at the sort of the place where the feldspar were. And we published an image in 2015 or whatever. It didn't track really much attention, but the apatite actually tracks the replacement of feldspars and biotite. Okay, excellent. Thank you for that.
Katerina, as our lone studio attendee, do you have any questions? Okay.
I was going to ask.
Do you think it's been covered off, or do you have any comment or question? Okay. All right, excellent. Oh, that's good feedback. Okay, well, Tobias, I think we've kind of exhausted our question time. Thanks everyone online for asking the questions and joining the seminar today. Tobias, thank you one more time for a great talk. It's really good to see that, and great to see some of the publications that you're going to produce from this. I think it's really important work.
Thank you for having me.
No, it's been great. Thank you so much. I guess the last thing I have to do is to advertise next week's talk, which is coming from Dr. Melanie Finch at Monash. She's going to be doing a remote presentation. Melanie is a 2021 to 2022 superstar of STEM, and she's going to be addressing a kind of an unusual topic for this seminar series, but something that is nonetheless really relevant to us as a kind of an industry, which is why we lose women from geoscience. And she's going to be presenting evidence-based causes and solutions. And I think that's really key as we move forward. So I hope you can join us next week. The registration for that will be out next week as well. Okay, but just from us here today, here in Brisbane, thanks again for joining us. Thanks, Tobias. Tobias joined us really early from Perth this morning, so we're going to let him get off and get some coffee. And
I had a coffee before the talk.
Oh, I think it worked. It went well. All right, great. Well, thanks, everyone. Goodbye.
Thank you, everyone. Bye-bye.